Welcome back for video 2 for convex lenses, and we are going to finish up with concave lens. Here we have a combination of two lenses. Okay, we have, in this case, the distance between our arrow and our first lens is actually going to be 30 centimeters. And then the distance between the two lenses, okay, is actually 20 centimeters. And then we're going to look at our focal lengths here. We've got the blue dots here represent the focal length, okay, for the first lens here, okay. And the focal length is 10 centimeters. Okay, and then the focal length for this one here is also 10 centimeters. So I'll label this F equals 10 centimeters, and over here F equals 10 centimeters. I'm not sure I've drawn mine to scale, so ignore the fact that the scale drawing is a little bit off there. Okay, so let's go ahead and figure out our ray tracing diagram. From our first lesson, you know, the first light ray, let's trace it parallel to the lens, and it gets refracted through the focal point to here. And then I just take one straight through all the way over there, and where they intersect, we're going to get this red arrow here, okay, to show that we have an upside down real image. Okay. Now what about our next lens? Well, this real image now becomes the object for the second lens. So even though it's an image, it's still something that could be treated now as an object. So how do we deal with that? Well, let's take one parallel to it, and that's going to get refracted through the focal point. And let's take another light ray up, and that's going to be refracted parallel. Okay, let's put our eye over here. So this is our eye looking in, and we're going to see the eye is going to think that this light ray came from over here, and this light ray here is going to get traced back. Okay, and where the two intersect is where our green arrow is going to be. Okay, it looks like I'm a little bit off there. Let's see if I can move that. Let's place it right there. Okay, and let's see if we can make that a little bit smaller and make sure that matches perfectly. There you go. So where the two light rays intersect, that's where our image is going to be. Notice that this one is still upside down as compared to the first one there. So we don't see a flipping going on because the eye has to look through the lens, and the second one is a virtual image. The first one's a real image. The second one is a virtual. So no inversion occurs in the second one. Let's take a look and see how we can calculate this. Let's deal with our first one here. We're going to calculate where the image should be formed. So I'm going to say 1 over 10, because that's the focal length, equals 1 over 30 plus 1 over the image. Okay, and doing this calculation, the image distance turns out to be 15 centimeters. So what that means is this red arrow is now 15 centimeters, okay, from this lens here. Let's calculate the magnification for that. The magnification for this is going to equal minus I over O. So we have minus 15 divided by 30, because 30 was our object distance. And the magnification for our first lens is then going to equal minus 0.5. So that means this red arrow here is going to be half the size as this black arrow. Now again, drawing not the scale, we're not actually observing that. It is a little bit smaller there. Okay, now let's figure out when you do the second lens. This red arrow now becomes the image or the object for the second lens. Well, there's 20 centimeters between the lenses, and this red arrow, the image, is 15 centimeters from that. That means our new object distance has to be 5 centimeters. So the object is going to be 5 centimeters. Remember, this is actually an image formed by this lens, but becomes the object for the second lens. So let's do our equation. 1 over 10, because our focal point is still 10, equals 1 over 5 plus 1 over image. And the image this time turns out to be a negative 10. Now remember, a negative 10, okay, because it's this green arrow, okay, is on the same side as our object. Let's calculate the magnification. The magnification for that has to be a minus 10 divided by 5, okay, which equals 2. Okay, so we're now going to get this green arrow should be twice the size as this red arrow. Again, not drawn to scale. So that's how we calculate the magnification of the second. Now the whole system will have a magnification total. How do we get that? We're going to multiply the two magnifications. We had a negative 0.5 and a positive 2. So magnification total, I'll just label it m sub t, is then going to equal a negative 0.5 multiplied by 2, which equals a negative 1.0. So what this means then is our final image, which is the green one here, which is only seen by looking through this way because that's a virtual image. This first image everyone can see because it's real. The second one is a virtual, only looking through the other side of this lens. This arrow should be the same size as this because the magnification is 1, but since it's a negative, it should mean it's upside down. So this green arrow is the same size as this, and within reason, because again, my drawing is not the best drawing for scale. Okay, but upside down, the negative means inverted when we're done. So we end up with the final image that is a virtual, but still upside down image because of the combination of the lenses. And that's how we deal with combinations of lenses. In our final video, we will look at concave lenses.